Spielman, Ida Tietzinger, and Charles Clark and Nicole Younger-Halpern are the permanent members of that group, and it's a pleasure for me to work with them on a daily basis. I also want to emphasize that I'm giving this talk partly under the auspices of the International Union of Pure and Applied Physics, which is an international organization of physics societies from all over the world, and one of the major forces behind the creation of the International System of Units, the International Metric System. And this talk is part of IUPAP's promotion of the new version, the reforms of the International System of Units. And as we go along in this talk, I want you particularly to think of questions to ask, because we're going to stop it several times during the talk to answer questions from the audience. So please post your questions to the chat. And if you want to, feel free to pose your questions in Spanish, and Tara will translate them for me. Okay, so the title of the talk is A New Measure, the Revolutionary Quantum Reform of the Metric System. Well, the metric system came into being with the French Revolution at the end of the 18th century, and the revolutionary reform that I'm talking about now is, I believe, the greatest revolution in measurement since the French Revolution. And this revolution happened, or it went into effect, on the 20th of May, 2019. And it's a revolution in how we define the 7 base units of the International System of Units. Our modern metric system is based on 7 units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And the nature of the revolution that we have just experienced is that today, every one of those units is defined by defining a fundamental constant of nature. Now, how can we define units? By defining constants of nature. Well, in order to see how this is done, and I'm going to use an example of an earlier unit of measurement that has not been changed, namely the unit of time, the second. And with apologies to the late, great Stephen Hawking, I'm going to bring you my version of a brief history of time. Well, since we have had seconds, we have defined the second as being a certain fraction of a day. That is, a second is 1 day divided by 24 hours per day, by 60 minutes per hour, by 60 seconds per minute, so that 1 second is just 1 day over 86,400. But by around the year 1900, we had already learned that the day was not constant, that all sorts of things were changing the length of a day. And so a second defined in terms of the length of the day was not really a very good definition. But it wasn't until much later that we, in fact, changed that definition using atomic clocks. Whereas the Earth may change its rotation speed because of the friction of the tides, or the redistribution of the mass of the Earth in earthquakes, or the changes in ocean currents, atoms and molecules don't change, at least as far as we know. And this clock, which was made in 1949, used ammonia molecules as the tickers for what was, in fact, the first atomic clock, although it was actually involved a molecule rather than an atom. And these atoms and molecules don't change, so they're better clocks than the rotation of the Earth. Here's a picture of the first cesium clock in 1959 in the United Kingdom, where the first of these clocks was made in 1955. And the way in which the clock works, or at least an oversimplified version of the way the clock works, is we have cesium atoms represented here with this cartoon. We have a nucleus and an electron, and both the nucleus and the electron are spinning and creating magnetic fields. And we shine microwaves in to that atom. And when the microwaves have just the right frequency, which is shown here, a little bit more than 9 gigahertz, then it causes the electron to flip its spin, because there's a different energy for when the electron and the nucleus have their spins lined up and when they have their spins in opposite directions. And when that energy corresponds to this frequency, then the electron will flip its spin. So you can tell that you've set the microwaves to just the right frequency when you see that the electron has changed its state. And so this allows us to define what we mean by a second by defining the frequency difference between these two states to be exactly this number. And in fact, this is still the definition of a second, that it's the duration of a certain number of periods, some 9 billion periods of the radiation that corresponds to the transition between these two levels of cesium. And since the time that people first started to make atomic clocks in 1955 until around the middle 1990s, the performance of these clocks has improved dramatically by something on the order of magnitude every 10 years. But this improvement was stalled at a bit better than a part in 10 to the 14. Now, you may say a part in 10 to the 14, that's incredibly good. And it is. But we're never really satisfied. We always want to do better. And in order to do better, we had to slow the atoms down. The reason we were limited to a part in 10 to the 14 is because the cesium atoms in the gas that we use to make this atomic clock are moving really fast, over 100 meters per second. And I and others were involved in learning how to cool these atoms down. And by making these atoms move not at 100 meters per second, but at less than a centimeter per second, cooling them down to temperatures lower than 1/1,000,000th of a degree above absolute zero, we were able to make these clocks work even better. So that today, these clocks are good to a few parts in 10 to the 16, making time the most accurately measured quantity in the International System of Units. But the concept here is very important. We went from something, the rotation of the Earth, that is somewhat arbitrary. It has no fundamental connection to the laws of nature, to an atom, something that is very fundamental, something that is in fact very quantum, and made the energy levels in this atom be the thing that we use to define what we mean by time. So this is going to be a common theme in what I'm going to tell you about, that we go from something that is basically an artifact, something that has no particular connection to the laws of physics, to the way in which nature is made, to something that does, namely, in this case, an atom. And so I want to stop here and ask if there are any questions that have arisen. And I've written a few possibilities for questions that you might be curious about, but I'm guessing that you have better questions than the ones that I'm suggesting. So, Tara, do we have any questions in the chat, or do you have any questions?
Well, not yet, but let's see. Feel free to ask questions. The chat, please. If not, then I would like to ask about the leap seconds.
Okay. Well, remember, the original idea of seconds was that it had to do with the rotation of the Earth. And when people decided how they would set their clocks, they decided to set their clocks so that in England, in a place called Greenwich, where there was an astronomical observatory, that noon, by definition, for that time zone would be when the sun is highest at Greenwich. Of course, solar time would vary from one place to another, but they decided to make the standard time be when it was astronomical noon in Greenwich. Now, one day was until the next time that the sun was highest in Greenwich. But when we redefined a time, it meant that we were free from synchronizing our time to the Earth. and the Earth was changing. And what that means is that if we don't do something about it, then noon is no longer going to be when the sun is highest in Greenwich. And so in order to keep astronomical time in sync with atomic time, whenever they get out of step by 9/10 of a second, then we make a change. And that change is called a leap second. And all of the leap seconds have been in the same direction, so that when we put in the leap second, we make the day 1 second longer. And this generally happens on New Year's Eve. So what it means is that if you're celebrating on New Year's Eve, and we happen to be in one of the years when we're putting in a leap second, you have an extra second to celebrate.
That's great. We have a question. How
Wonderful.
much cost the least expensive atomic clock?
Ah, yes. Well, that's a good question. I'm not sure that I know what the least expensive ones are, but if you want a cesium clock, then it's going to cost about $100,000. I think there are cheaper rubidium clocks. So cesium, the reason you want cesium, of course, is because the definition of the second is based on cesium. But rubidium, while it doesn't, the definition of the second is not based on rubidium, we know the ratio well enough that a cesium clock is going to work very well for you. And those rubidium clocks are not as costly as the cesium clocks, but I don't know what the price of them is. Now, I should say, you might sometimes find that you're in a store and somebody is advertising an ordinary clock that they say is an atomic clock. It's not. What it is a clock that receives radio signals from the actual atomic clocks and synchronizes itself to the atomic clocks. So to the resolution of these clocks, which is typically on the order of a second, you can be sure that it's keeping time as well as the atomic clocks, but it's not really an atomic clock.
Okay. So far, no other questions.
Okay, let's go on. So we've had a short history of time. Now I'd like to tell you an even better story, which I'm calling a short history of length. Now, time was important historically for lots of reasons, but length was even more important because it had to do with commerce, with trade. There was real money involved with length. And the earliest standards of length were related to the human body. A foot was the length of your foot. A cubit was the length between your elbow and the end of your hand. Well, this was wonderful because it was very convenient. You always had your standard of measurement with you, but it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might not get what you expected. So how could we solve that problem? Well, one of the ways in which this problem was solved was to fix the unit to the body of a particular person, usually the king, or in the case of ancient Egypt, it was the pharaoh. And in ancient Egypt, they did exactly that. They defined something called the royal cubit, which was based on the length of the pharaoh's forearm. Now, you didn't always have the pharaoh around when you wanted to make your measurement. And so they made an artifact, a piece of stone that was the primary standard of length for Egypt based on the size of the pharaoh's forearm. And they used that, or they used wooden replicas of it to build the pyramids, for example. And the people who were out in the field measuring the stones for the pyramid were required to recalibrate their wooden standards against the stone standard cubit at least once a month. And the penalty for not recalibrating was the death penalty. So these people were really serious about their metrology, and the results showed that seriousness. The baselines of the pyramid are good to a tiny fraction of a percent. They're square, the pyramids are square to 12 arc seconds of angle. So they really did succeed in doing an excellent job of metrology. And similar artifacts, length standards, were very common in Europe. And each town might have fixed into the wall of the town square the standard of length. And you can see here, uh, this is the town of Regensburg in Germany, and a tourist is measuring her fathom against the length of the standard fathom in Regensburg. And you can see here, the fathom was quite generous. So this might be a good place to buy fabric. But if you were to go to a different town nearby, you would have a different standard of length. So this was a rather annoying situation that every place you went had a different standard of length, even though it would be consistent for that particular town. So at the time of the French Revolution, the French revolutionaries decided they would fix this by choosing a standard of length that was good for everyone. So they decided that the new standard of length, which they called the meter, would be 1/10,000,000th of the distance between the North Pole and the equator on a meridian that passed through Paris. And the idea was that this new standard of length was going to be something that would be available to everyone, since the Earth is available to everyone, and that it would be good for all time, since the Earth should be something that endures. And so what they did was they sent out a team of surveyors to determine the distance along this meridian between Barcelona in Spain and Dunkirk in France. And this was supposed to be a measure that would be good for all time, for all people. And they made this medal to commemorate the idea. You see this mythological creature symbolically measuring the Earth, and that's exactly what they did. They measured the Earth, and these surveyors came back with a new unit of measure, the meter. But of course, it wasn't very convenient to always go back and measure the Earth. So they took this measurement that had been made by these surveyors, and they made an artifact, just as the ancient Egyptians did. And this metal rod made out of platinum became what was called the meter of the archives. They deposited it in the archives of France, and it became the standard meter for the entire country of France and for all those other countries who adopted the metric system. And then some decades later, in 1875, there was an international meeting at which they devised a treaty so that all of the countries attending and signing this treaty would agree that the meter was their standard of length. And they made a new meter, platinum iridium bar, and they put 2 scratches on it that were as closely as they could measure the distance corresponding to the length of the old meter of the archives. So this became the new meter, the international prototype of the meter, and the standard of length for the entire world. Now, this was the late 19th century. And in the late 19th century, people had learned that light was a wave. And they had learned ways of measuring its wavelength. Here is a cartoon version of an interferometer called a Michelson interferometer. And the idea is that you have a source of light, it comes in, it bounces off a half-silvered mirror, what we call a beam splitter, so that some of the light went in this direction and some of the light went straight through in this direction. And in each of these cases, there were mirrors that bounced the light back. And the 2 beams of light, the one that went to this mirror and the one that went to this mirror, would interfere and produce this beautiful interference pattern in the place where the crests of the waves of light would line up. The light would be very bright, and the place where a crest of one beam corresponded to overlapped with the trough of another beam, the light would cancel out and you would get a dark spot. And if you move this mirror by 1/4 of a wavelength of light, it would change this from being dark to light, which was easy to see. That means it was easy to see a measurement, a movement of the mirror of just 1/4 of the wavelength of light, which was about 2/10 of 1/1,000,000th of a meter. The scratch on the meter bar was about 20 millionths of a meter wide, and you had to decide where the middle of that scratch was. So clearly, this interferometer was a better way of measuring length than you could achieve with anything involving the actual meter rod. So what happened was that people began to use light as a kind of de facto standard. When they measured the length of something, they would report what it was in terms of the wavelength of some light, and they would give the best estimate of what that was in meters. But in fact, it was more accurate to measure it in terms of the wavelength of light. So what that meant was that we had a technology, namely optical interferometry, that was more accurate than the definition of the thing that the technology could measure, namely length. So that meant that the definition of length needed to be changed. And it took a long time before they did change the definition. In 1960, which by the way was the year that the laser was invented, the meter was redefined to be a certain number of wavelengths of light from a krypton lamp. You have a gas of krypton inside this lamp, and you put an electric current through here, and it would give off a very pure orange-colored light, and that became the new standard of length. But remember, this was the year that the laser was invented, and it didn't take long before laser light was understood to be even more pure than the light that was coming from these krypton lamps. So again, we had a situation where we had a technology, namely the laser, that was better than the definition of length, which was based on the light from this lamp. So people were doing interferometry with laser light and reporting their results in terms of the wavelength of a laser like this one, instead of in meters as defined by a krypton lamp. And again, it seemed that we needed to change the definition of the meter. Now, the obvious thing to do would have been to redefine the meter in terms of the wavelength of this laser. That would have been the obvious thing to do. But fortunately, they did not do the obvious thing. They did something that I think was both beautiful and brilliant. They defined the speed of light. Well, why does defining the speed of light make things work better? Well, by this time, which was around 1983, people had learned how to measure the frequency of light. Light is an electromagnetic wave, just like radio waves and microwaves. And by 1983, people had learned how to measure the frequency of oscillation of light waves, which is close to 10 to the 15 cycles per second. So if you can measure the frequency of light, and if you define the speed of light, then this universal expression that the wavelength times the frequency is equal to the speed of light allows you to know what the wavelength of light is for any light for which you can measure the frequency. So since they had learned how to measure the frequency of light, by defining the speed of light, they knew what its wavelength was, essentially perfectly. And so the new definition of the meter is that the meter is the length of path traveled by light in a certain fraction of a second. And this number that's in the denominator is the speed of light in meters per second by definition. So this was wonderful. Any light that you can measure the frequency of becomes a new standard of length. If someone makes a better laser where the light is more pure, then this definition already covers that. If someone figures out how to measure the frequency of light better, then this frequency covers that. And people did that. These gentlemen, Jan Hall and Ted Hench, learned how to make better lasers. They learned how to measure the frequency of light better, and they revolutionized the measurement of length. And it was already taken care of by the new definition of length. So now we have a concept that's even more beautiful than the previous one, where we went from an artifact to a natural standard, an atom. So this was going from an artifact, the length of a platinum iridium bar, to something natural, an atom emitting a certain wavelength of light, to something that's universal, the speed of light. And the beauty of this is that we should never need to change the definition again, because the definition is now based on a universal and fundamental constant of nature, namely the speed of light. So, as I said, this definition of the meter is both brilliant and beautiful, even more beautiful than the definition of the second. And on the 20th of May, we redefined the international system of units by bringing this same beauty to a new definition of the kilogram and to the ampere, the Kelvin, and the mole. So why did we have to do that, and how was it done? Well, I'm going to tell you that story in a moment, but first I want to see if there are any questions about length, or if you've thought of any questions about time.
We do have a new question about time.
Wonderful.
So, in which way gravity affects the definition of time?
Yes, perfect. So it turns out that in 1915, Einstein came up with a new theory of gravity that we call the general theory of relativity. And part of that theory predicted that if you had a clock in the gravitational field, like the gravitational field of the Earth, and if you raised the clock so that it was higher in the gravitational field, that it would run at a faster rate. And a clock that's lower in a gravitational field is going to run at a slower rate. So one of the things that it predicted was that a clock on Jupiter, where the gravity is stronger, would run slower than a clock on the moon, where the gravity is weaker. And that on Earth, you would have a different clock rate for a clock that is at sea level than you would have for a clock that was on the top of a mountain. Now, the effect is extremely small. If I raise a clock by 1 meter, that changes the clock ticking rate by only 1 part in 10 to the 16. So what that means is these cesium clocks that I've been telling you about that are good to a few parts in 10 to 16 will not be able to tell that you have raised one of them by 1 meter, because it's below the uncertainty level of that cesium clock. But the amazing thing is that today we now have clocks that are better than cesium clocks, and perhaps I'll have a chance to speak about them a little bit at the end, that can tell the difference of moving the clock by just 1 centimeter. When I was very young and first started working at NIST, the best clocks were cesium clocks that were good to a part in 10 to the 13. We've improved by a factor of 1,000 since then. And I've gotten a lot older since then. And I am very proud that I was able to contribute a little bit to those improvements. But if we had had 2 clocks, one in Washington, which is close to where I work, and one in Boulder, Colorado, which is up in the mountains, where the best clocks are still today, we would only be able to just barely see the difference between 2 clocks that were separated by more than 1 kilometer, about 1.5 kilometers. And today, we can see the difference of 1 centimeter or less. So that tells you something about how amazingly accurate today's clocks are, how much they have improved, but also this really strange feature that it depends on where the clock is in gravity's field, how fast it ticks, which raises the question about how we're going to define what we mean by time when clocks can detect the position of where they are to better than a centimeter, and things like sea level and the distribution of water in the earth are changing because of climate change. What will that mean for the definition of the second? Those questions have not yet been answered. Thank you for that question. That was a wonderful question.
We have another one. So how do you measure the uncertainty level of an atomic clock?
Ah, yes. Well, there are two ways. One way is that you think of all of the things that might affect your clock. Let's say you wonder, well, will a magnetic field affect my clock? Well, we know that it does, at least a little bit. So one of the ways we can do that is we can apply a known magnetic field and see how much it shifts the clock, and then try to shield the clock from magnetic fields and make a measurement of how well we've done, or at least put a limit on how small the magnetic field is. And now, if, say, we know how much one microtesla shifts the magnetic field, and then we know that we have shielded the clock to 1/10 of a microtesla, we can know what the uncertainty is, or we can calculate what the uncertainty is. We can, let's say we make repeated measurements on the clock and we see how much they vary from one measurement to another. That kind of statistical uncertainty is something that we can factor in. So this way of doing things, we either measure or we calculate all the sources of uncertainty that we can think of. So let's say, for example, that the clock is an ion that it's one of the ways in which we make clocks is an ion, and it's close to some metal, and we don't know how that metal affects the clock exactly. We change how far away the ion is from the metal, measure what it is, and then we can assign an uncertainty. You add all of these things up and you say that's your uncertainty. That's one way of doing it. The other way is that you compare your clock to another clock that is made in a different laboratory, that is measured by different people, and you compare the ticking of these two clocks. These are very different ways of measuring the uncertainty. And if the two ways agree, that is, if when I add up all the ways in which my clock might be wrong, and I say, well, I think it's wrong by, it could be wrong by as much as 3 parts in 10 to the 16, and then I compare it to someone else's clock, and I find that we're different by 2 parts in 10 to the 16, then I'm going to say, not so bad. But if I'm wrong by 10 parts in 10 to the 16, then I'm going to say, oh, this doesn't look so good. Maybe we need to do some more work. So those are the ways in which we learn about how good our clocks are. And today, we think these cesium clocks are good to about a few parts in 10 to the 16, using those kinds of approaches.
No further questions.
Okay, excellent. Let's go on. So now I'm saying that we're going to do this same thing that we've done to first time and then length. We're going to do it to mass. So here's my light history of mass. So here is a picture of some ancient mass standards from ancient Babylonia. These are stones that have been polished, and they formed the standards of mass for the for Babylon. And one of these stones, I forget which one, is called a shekel, a term you might have heard, that was a mass that was used for the mass of some precious metals that were used to make coins. The trouble was that, as with other kinds of artifacts, these artifacts might vary from one place to another. So the French revolutionaries decided they would fix this and fix it by using the meter. So they said, let's take a volume of water that is 1/10 of a meter on a side, and let's say that we're going to call the mass of water of that volume 1 kilogram. The trouble was, it wasn't so easy to measure the mass of 1 liter of water, and so they made an artifact. And here is the kilogram of the archives. It became the mass standard for France in 1799. And in 1875, when they had this international meeting where the countries of the world agreed to adopt the metric system, then they also agreed to make a new mass standard. And there it is. That's the international prototype of the kilogram. And it was made to be as close as possible to the mass of the kilogram of the archives, which was made in 1799. Now, I want you to think about this. This, up until 2019, was the definition of the kilogram. That the kilogram is the mass of the international prototype of the kilogram. We are in the 21st century. The unit of mass was an artifact, a piece of metal that was made in the 19th century, and it was based on an object that was made in the 18th century. I think it is scandalous that our definition of the mass was based on such an antique way of doing things. Think about this. If someone left a fingerprint on the international prototype of the kilogram, everyone else in the world would lose weight. Now, nobody has left a fingerprint on the international prototype of the kilogram, but it appears that its mass is changing. Here is a plot of the mass of a number of copies of the kilogram made at the same time in exactly the same way, measured relative to the kilogram itself. And you can see that almost all of them are going in the same direction, which might make you think that the kilogram is changing its mass, that the kilogram is getting heavier because all these copies, it looks like the kilogram is getting lighter because all the copies look like they're getting heavier. But of course, the kilogram can't be getting lighter or heavier because legally it's always a kilogram by definition. Well, this is scandalous, obviously need to be fixed. And the way in which the international community decided to fix it was by fixing the value of a fundamental constant in the same spirit as what was done to redefine the meter, namely defining the speed of light. So what is the constant of nature analogous to the speed of light that we're going to use? Well, in order to understand that, let's think about this famous equation, probably the most famous equation in history, E equals mc squared. The energy of an object is equal to its mass times the square of the speed of light. What does this mean? That if we have an object at rest of mass m, that its total energy is equal to mc squared. Now let's look at another equation. This is the energy of a photon, a particle of light. It's equal to Planck's constant times the frequency of the light. And as we've mentioned before, we know how to measure the frequency of light very well. So if we were to define Planck's constant, that means we would know the energy of a photon. So what if we take that energy and make it equal to mc squared and solve for m? What that means is that there is a mass that is in fact the change in mass that a particle will experience if it emits a photon with frequency f. That change in mass is going to be Planck's constant times that frequency divided by the speed of light squared. So this means that if you've already defined what the speed of light is, if you in addition define Planck's constant, then that means you have a new way of defining mass based on how much the mass of some particle, let's say a nucleus, changes when it emits a photon of a certain frequency. Now, this isn't the way we're going to do it. We're not weighing photons. We could and we do, but we just can't do it well enough. But instead, we're going to use Planck's constant to define the kilogram. And this expression is simply to indicate that if we do define Planck's constant, it gives us a way of getting to the mass. But we're not going to do it by weighing photons. Instead, we're going to do it by seeing how fast an atom recoils when we hit it with a photon. So here's a cartoon of an atom. Let's say it's in its electronic ground state, and we shine in a photon that can excite it to an electronically excited state. We can measure the frequency of that photon. Because we can measure that frequency, and because we are defining Planck's constant, that means we know what the momentum of the photon is, because the momentum of the photon is equal to Planck's constant divided by its wavelength. And we know what the wavelength is because we know the frequency, and we know what the speed of light is, which we've defined. We know what the wavelength is. So we've got an atom. We hit it with a photon. It goes into the excited state because it absorbed the energy of the photon, which is h times the frequency of the light. And it also absorbs the momentum of the photon. So now it's moving with a velocity that's equal to Planck's constant divided by the mass times the wavelength, because just of conservation of momentum. So that means the mass of the atom is equal to Planck's constant divided by the velocity and the wavelength. Now, we were defining Planck's constant. We've essentially measured the wavelength because we can measure the frequency. We're going to measure the velocity by measuring the Doppler shift, and we've gotten techniques to do that very accurately. That means we know what the mass of the atom is. Now, it's really important to think about what this means. We know what the mass of the atom is in kilograms. We have measured for many decades the masses of atoms in what's called atomic mass units. That means we've compared the masses of something like rubidium, which is the atom we usually use for these experiments. We've compared the mass of rubidium to the mass of carbon, which is the thing that defines what the atomic mass is. The atomic mass of carbon is defined to be 12. Okay, so we knew what the mass of atoms was in atomic mass units, but now we know what the mass of a single atom is in kilograms. Now, if we could just multiply that up to the number of atoms that would equal a macroscopic mass, then we know what the mass of that macroscopic object is if we know how many atoms are in it. Here is that macroscopic object. This is a single crystal of silicon. Silicon, because the semiconductor industry has learned how to make single crystals of silicon really, really well. It's also isotopically pure, which makes this thing really expensive. But at the metrology laboratory in Germany, called the PTB, they have made a single crystal of silicon into a sphere and measured the spacing between the atoms in that perfect crystal and the size of the sphere. That means they know how many atoms are in that sphere, how many silicon atoms. And we know the ratio of the mass of silicon to the ratio of the mass of rubidium because of all these experiments that we did measuring atomic mass units. And because we now know the mass of rubidium in kilograms, that means we know the mass of silicon in kilograms. And that means that if we know the dimensions of this and the spacing between the atoms, which we measure by X-ray interferometry, we know how many atoms are in this perfect sphere. And therefore, we know what the mass of this sphere is. This sphere is not an artifact. This sphere is something that anybody who has the right skills can reproduce. Whereas in order to reproduce the international prototype of the kilogram, you would have to have a copy of that international prototype of the kilogram. You can start from scratch and make a sphere like this and make it to be a kilogram. So this is a new way of making a kilogram by defining Planck's constant. Now, it turns out that there are other ways, and I'm not going to have enough time to go into this in detail, but let me just show you a brief idea of how this works. This is a thing called a watt balance or a Kibble balance. the guy in the previous slide was named Brian Kibble. And first, I want to remind you of the way that traditionally we measure mass. We have an unknown mass here. We have known masses on the other side of the balance. And we keep putting known masses on one side of the balance until the balance balances. And then we know that the unknown mass is equal to the sum of these known masses. We've measured mass that way all the time. But now I want to invite you to think about a different way of measuring mass. Instead of putting a known mass on, let's put a coil of wire that carries current. Sorry, I don't know why that switched, but let's go to this again. Okay. Now we should be right. Okay, now I'm going to try to fast forward this. Okay. Anyway, so that's the traditional way of measuring mass. Now let's imagine that instead we put a coil of wire, and the coil carries current, and it's immersed in a magnetic field. So there's a force on this coil due to the current operating in a magnetic field, and we can compare that force to the gravitational force of the unknown mass. Now, because we know how much force a current of wire generates in a known magnetic field, if we know how much current there is, if we know where that current is, and if we know exactly what the magnetic field is and which way it's pointing, then we could calculate what the force is, and then that would tell us what the mass is. Trouble is, we don't know how to measure all those things well enough. But here's where the genius of Brian Kibble comes in. What Brian Kibble said was, okay, that's great. We could imagine doing that. Now let's imagine something else. Let's imagine that we take that coil of wire and we, as before, have it in a magnetic field, but we take the leads of that coil of wire and connect it to a voltmeter. And now you see we're going to move the coil at a certain constant velocity, and that's going to generate a voltage. This is like what a generator does. So we're going to measure that voltage very accurately, which we can do very well. We're going to measure the velocity really accurately, which we can do very well. And this measurement is called the velocity mode. So we measure the velocity, we measure the voltage. And then we do the thing that we've always done. We take that same coil of wire, we send current through it, and we can measure the current very well. And we measure the force compared to the gravitational force of the unknown mass, and we call that the weighing mode. Now, the beauty of this is that if we take the mass from the weighing mode, multiply it by the acceleration of gravity, multiply it by the velocity that we had in the velocity mode, so the other experiment, that's got to be equal to the current from the weighing mode times the voltage generated in the velocity mode. Why? Because the mass times gravity, which is a force, times velocity, that's mechanical power. And current times voltage, that's electrical power. This is watts of mechanical power. This is watts of electrical power. Those two things have to be the same. And because they're the same, it means we can solve for the mass. And that means that this mass that we didn't know what it was is equal to the current times the voltage divided by the acceleration of gravity times the velocity. Now you might say, well, wait a minute, what does this have to do with Planck's constant? And the answer is that we're going to measure the current and the voltage in a quantum way that's going to require Planck's constant, because Brian Josephson, shown here, told us the relationship between Planck's constant and voltage, and von Klitzing told us the relationship between Planck's constant and resistance. And if we measure the current and the voltage using von Klitzing's way of measuring resistance and Josephson's way of measuring voltage, we're going to get the mass in terms of Planck's constant. And here is a picture of that balance, which does that. It realizes the kilogram to about a part in 10 to the 8th, which is about as much as these kilograms are changing from 1 year. It was better than how much these kilograms are changing from year to year because of, well, we don't really know what it's because of. And here's the team at NIST who did that, and they're so confident in their measurements that they've tattooed the new values of the fundamental constants into their arms. Now, I'm going to stop here and ask for questions, and realizing that I went through this description of the Kibble balance very fast. So if you have any questions about that, I'll be happy to answer, and then we'll finish up. So, any questions?
But I think that the best question is, why were you wearing a winter coat in the picture with the kilogram?
Right. So let's go back to that if I can show you that. This was a picture of me in the archives of France. So remember, I told you about the kilogram of the archives and the meter of the archives. I was in the archives, and that is the kilogram of the archives. Now, when they made the archives, they realized that temperature control was really important for keeping everything in good shape. But this was 17 something when they built the archives. It was the end of the 1700s when they made this kilogram. And they did not have heating and air conditioning the way we do. So what they decided was that the best way of doing things was to make the walls of the archives extremely thick, so that the temperature would change very, very slowly. And this, they hoped, would make everything work very well. Well, I visited late in the winter, and by then, the temperature had slowly changed from the summer temperature when it was warm to the winter temperature when it was cold. And we all had to wear coats in order to be comfortable because there was no heating and no cooling in the archives of France. They just were trying to keep the temperature from changing very rapidly. And that's why it was so cold.
We do have a question from the public. If it's easier now, the traceability process from national standards to the new international mass standards definition for the country's national labs.
Yes, well, I'm not sure that it's very much easier. The main thing that has been gained is that it's stable. So the way in which national labs would check their traceability to, say, the international standard is they would take their copy of the kilogram, which they'd gotten from the International Bureau of Weights and Measures, the BIPM. They would take it to the BIPM and compare it to the standards kept by the International Bureau of Weights and Measures. That's how traceability was handled to the international standards. The trouble was that the standards that the BIPM had were changing for reasons that no one really has yet understood, but perhaps we will. What we can guarantee now is they won't change. So it's not as if it's going to be any easier. We're still going to have to carry around platinum iridium kilograms, but we're going to be able to say, we know that this kilogram is the same compared to what it was 20 years ago, because it's been checked against either a silicon sphere or against a Kibble balance. So, and the people at the BIPM are making those checks, or people in other laboratories. Of course, if you're in a laboratory that you have a national metrology laboratory that can make the silicon sphere or that can make a Kibble balance, then you don't have to worry about tracing your result to the international standards laboratory. You can do it in-house, and but it's probably not as easy as carrying your kilogram to Paris. It's this comparison against the silicon sphere or against the Kibble balance is really quite involved. And so probably not every standards laboratory in the world is going to have such balances, but the ones that do don't need to worry about the international comparisons.
Okay. One question, these methods assume that conservation laws are absolutely true.
Yeah, that's true. And so if it turned out that for some reason that momentum, say, for example, that momentum is not conserved, or that gravitational mass is not the same as inertial mass, or that for some reason mechanical momentum is not the same, or mechanical power is not the same as electrical power, then we would have to rethink these things. But we have no reason to believe that that isn't true. We've tested a number of these assumptions. And as far as we can tell, for the moment at least, as well as we can measure all of these conservation laws, all of the constancy of the so-called constants of nature are as good as we can measure for the moment. We keep checking, but for the moment, everything is okay. So what that means is that we can be confident that as well as we can measure things, that the standards of measurement that we use are still valid, but we keep checking.
No further questions?
Okay, so let's go on. So now people around the world were measuring masses using either the silicon sphere method or the Kibble balance method. And here's a map of laboratories around the world that were measuring these things. And I think there are probably more points on this map today than there were then. And when everyone was agreeing, so what they were doing was they were measuring Planck's constant. When everyone agreed on what the value of Planck's constant was, then they turned the experiments around and said, now we're going to define Planck's constant. And these experiments that used to be a measure of Planck's constant are instead going to be a way of, well, they met in Versailles in 2018 and voted as to whether they were going to do this change. And this is what they showed.
140 years.
Groundbreaking science.
And the agreement from the world scientific community.
This is the movie they showed when everyone had voted unanimously to make this change.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it. Ce l'abbiamo fatta. Wir haben es geschafft. Lo logramos.
Lei sia buoni.
Biz bundan ayrı olduk. Proud am die.
Biz bunu já saber. Het is ons gelukt.
Biz geleden.
Tasarım.
Vi gjorde det. Nismo to učinili. Dokázali jsme to. Congratulations. Candida. Felicitaciones.
Bazzaito. Congratulazioni.
Šate realization. Selamat sukses.
Parabéns.
Ongela. Omedeto.
Amguida.
Onneksi olkoon.
Mabruk. Kapai.
Aiko.
Félicitations. Congratulations.
So when I see that, it gives me hope that if 60 countries in the world can unanimously agree on something, then maybe there's some hope for the future for international relations, which seem to be so fraught and so difficult today. Well, the story is almost over. In addition to redefining the kilogram by defining Planck's constant, the ampere has been redefined by defining the charge of the electron. So now an ampere is a certain number of electrons per second. We don't do it that way. We don't count electrons, although we're working on it. But now you see, because H has been defined and because E has been defined, it means that the Josephson constant, 2E over H, which is in hertz per volt, and H over E squared, which is in ohms, are exact in the International System of Units. And that means that we can use them to measure electrical quantities in the International System of Units. We've also redefined the mole. It used to be that the mole was the amount of substance that had the number of elementary entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. But now it's just a number. The Avogadro constant, Avogadro's number, is exactly this number of atoms per mole. And similarly, we've redefined the Kelvin. It used to be that the unit of temperature was 1/273.16 of the triple point of water. Now, the Kelvin is defined by defining Boltzmann's constant, a certain value of joules per Kelvin. What this means is that we have a microscopic way of defining what we mean by temperature. The temperature of a gas is now able to be measured by measuring the energy of the individual constituents of that gas. We're not yet measuring things that way. Well, we are, we're just not doing it well enough. But I'm hopeful that one day temperature will be defined by the velocity of atoms in a gas. And so the French Revolution brought us the metric system with meters as the measure of all things. The measure of length, kilograms as the measure of mass. The International Treaty of the Meter gave us an international agreement about units. And on the 20th of May, 2019, which is the anniversary of the signing of the Treaty of the Meter, we had the biggest revolution since the French Revolution. And that revolution means that we're now free of artifacts of measurement. All the base units are defined by fixing the values of constants of nature. And it seems that we have finally realized the dream of the French revolutionaries to have something that is good for all time and for all people, except possibly for time itself, because time is still tied to a specific atom, namely cesium, rather than to a fundamental constant. And we now have atoms that are giving better time than cesium. Atoms like calcium and mercury ions and ytterbium ions and ytterbium atoms and strontium atoms, aluminum ions, mercury ions are having atomic clocks that are better than the best cesium clocks. And so we're going to have to redefine the second sometime in the future. So what that future will be, I don't know. Only time will tell. Thank you very much. And so here's some possible questions about time that we've already talked about. Well, let's see, actually, I'm not sure whether time, I really wanted to talk about, let's see, length and mass. There's the old things about mass, or there are general questions about this talk. So if there are any questions of any sort, I'm happy to answer them. I realize that it's now more than an hour that we've been talking, but I'm willing to hang around and answer any questions that anyone has.
We have a question. How length is actually measured using the definition?
Yeah, exactly. So the way it's measured is you take a laser and you measure the frequency of that laser. Now, because of these advances that people like Jan Hall and Ted Hench made that got them the Nobel Prize in 2005, you can measure the frequency of these lasers in terms of the frequency of a cesium clock. The way it's done is you make what's called a frequency comb. You have a mode lock laser that puts out a series of pulses, and that, when you Fourier analyze it, that's like having a whole set of different frequencies. And the difference between those frequencies is a multiple of that difference is equal to each one of those frequencies. So you can, the repetition frequency can be compared to the cesium frequency, and that means you then know what the optical frequency is, and that means you know what the wavelength is because we defined the speed of light. Then you just use an interferometer, like a Michelson interferometer, like the one that I showed the cartoon of, to measure your length, and that's how you measure length in the new system. It's basically the way we've been measuring since the end of the 19th century. The difference is we now know what the wavelength of the light is based on the speed of light and based on measuring the frequency. Whereas before, they had to compare the wavelength of light to the meter bar, and that simply wasn't accurate enough. Now it's plenty accurate to, as we know the wavelength of light very, very well, and it's easy to then use an interferometer to measure the length of things. And that's how, for example, they measure the size of the silicon sphere, by using interferometry.
We have another question. So ampere is defined with the units coulomb per second. Do you think
Yes.
it is reliable to try to define as a basic unit the coulomb, so charge, instead of ampere, current?
Yeah. Well, that's a very good question. So let's see. Here we are. Right. So, in fact, there was a lot of discussion when people were trying to decide how shall we define what the new international system of units is. Shall we change from having the ampere being the base unit to having the coulomb be the base unit? You see, either one would be fine because the second is very well defined. So whether we define the coulomb to be a base unit or whether we define the ampere to be a base unit, it's just as good. What should we do? What will be the most convenient thing to do? And people decided, let's keep the base units the way they have been for a long time, rather than changing to make the coulomb be a base unit. As far as the accuracy, it really doesn't have any effect on things. The accuracy is the same. Now, one of the things that this question brings up is that the question of what units are the base units of the International System of Units. Here's the symbol. You see, we've chosen 7 base units. Why those? That was an arbitrary choice. And it could have been different. It could have been, as we've just said, it could have been the coulomb instead of the ampere. So one way of thinking about the new change is that base units are nothing special anymore. That the new SI is just the system in which each of these fundamental units, or each of these fundamental constants, has the values that are specified in the new SI. Planck's constant, the speed of light, the Boltzmann's constant, all of these, the charge of the electron, all of these things have certain fixed values in the International System of Units. And then you can simply say that the International System of Units is that system in which the constant have these values, and not specify which ones are the base units anymore. So we may, in fact, make that change sometime in the future. But for the moment, we have base units, and we've decided to keep them the same, even though it might have made sense to change them. But that was a choice made for convenience, not something based on the laws of physics.
Well, I guess this is more of a funny question, but as an American, how do you feel about the imperial system?
Yes. Well, one of the things I'd like to point out is that the International Treaty of the Meter, 1875, the countries of the world, I think there were about 17 or 18 countries of the world, came to Paris to discuss the International System of Units, what we now call the International System of Units, what they call the metric system. And they agreed that they would fund the International Bureau of Weights and Measures, and that the artifacts made by them would become their standards measurement. The United States was one of the original signers of that treaty. So that means, based on that treaty, the United States has been metric since 1875. In fact, we have been metric even earlier than that legally. we have not kept standards based on inches and pounds since the middle of the 19th century. That is, the inch and the pound were defined in terms of the meter and the kilogram from the middle of the 19th century. So this idea of so-called imperial units is, again, just something that is being done for convenience because people are resistant to learning about the metric system. Legally, we are metric just like the rest of the world.
Well,
And I wish we would change so that our day-to-day lives are also metric. It's funny because if you go to a supermarket, you buy soda, like, Coke or Pepsi or something like that, metric, and you buy milk, imperial. Now, why is that?
well, Dr. Phillips, thank you so much for this beautiful talk. It seems that we don't have any more questions. I hope that someday we can have you in person here in the Dominican Republic. And thank you so much for everything.
It would be lovely. I look forward to visiting the Dominican Republic and this historic university in person someday.
Well, everyone, thank you for coming. We will